Any numbers? No numbers, huh? Second bench, any expectation? What's about this side? So if you don't tell, I won't tell the number also. How much you expect? Average will be how much? 6, huh? Who said 6? That's also nobody will less than. So I won't tell the number if you don't say that. Okay, fine. But only thing I will tell you that some people did very good manipulation in the sense, the people who did very well in the first quiz, they thought anyway will be writing gate exam, why to write? Nothing they wrote, all wrong. I know that one person did very well in the first quiz, got 3 marks in the second quiz. Another person got 2.5 the second quiz. Okay? The highest was actually more than the first quiz. It's very interesting. So if you see the standard deviation, it will be very high this time. Highest is higher than first quiz. Average is lower than the first quiz. Very interesting. Highest is more than the first quiz. Average is lower than the second quiz. Number of zeros also there. Some people got 0 also. First quiz some people got 0 also. Okay. So based on that, I have decided that I will not give any U grade. Maybe the cutoff for the E grade will be 10 marks. 10 out of 10. 10 means what? If you attend the classes, you get 10 marks. No need to write. So I have decided if you get quiz 1 0, quiz 2 0, end semester 0, but you attend all the classes, you will get the pass grade. The very easy way to pass. Right? Because I am not going to issue any U grade. U grade means you have a chance to improve your grade. E grade means you have no chance to improve your grade. You are completely finished by yourself. That's what I wanted. I wanted you to finish by yourself, not by me. If you give U grade, if I give U grade to you, you will get a benefit. That benefit alone will not be given. So E is assured to all of you. Okay, so that's what I am telling you. So the answer sheet will be given some of the class hours, because within the class hours it is difficult because it takes almost 1 hour. I will see by Wednesday it can be given or not. If you can have some free time Wednesday. Around lunchtime, any class is there? Lunchtime means 1 o'clock, 2 o'clock, 3 o'clock. So maybe lunchtime 1 to 2. So Wednesday lunchtime 1 to 2 I can actually take the, if I am in station, I will actually try to give the answer. Lunchtime, what's the last class for you guys? Wednesday. 12 to 1. Then after that you are free fully. 1 to 6 o'clock you are just sleeping time only. Okay. So next time onwards, if I take extra class on Wednesday, I can take 1 to 2:30. Is that okay? That's better. Then you don't have to come all the way evening time. We can have full sleep after 2:30. 2:30 you say 8:30 you can sleep 6 hours. Then take food again you sleep. Better, no, good for health. If you sleep more, doctors say that is better. Good for health. Another thing is that Basudha, you have done generalized eigenvector. Okay, you put alpha equals to 0. But generally I said alpha equals to non-zero is better. That's what I never put alpha, that when you need when the noun space alpha equal to 0 I never put. I always put alpha equals to 1. In that way, Kavya or Srivalli, who is Srivalli? Yeah, we both have done very good job in that problem. So maybe Kavya can give me that problem to me. Work out. You have the, I think Basudha has the problem. You can actually take the problem and reword. The way you did it is very good. You got of course 5 out of 5 in that question. You also got, because alpha equal to 0 satisfies the general eigenvector. In that way both are correct, but it's not the right way to do it. You have to be very careful. Of course, your generalized eigenvector satisfies means I am supposed to give the full marks, and of course the marks is given. But most generalized alphas to be non-zero. That is the way to be demonstrated. So in that way, Srivalli, Kavya both have done. I think 1 or 2 more guys did really good job. Okay, so I think based on that, I think if I am in station Wednesday, maybe 1 to 2 I can give the answer sheet. Okay, so we are talking about the partial differential equation. So we have discussed in the last class the parabolic, hyperbolic and elliptic. We have seen the elliptic equation is having the elliptic equation has the equilibrium problem, parabolic problem has time dependency, and the hyperbolic problem also has time dependency. So parabolic problem at time to infinity will transform to the elliptic problem. Parabolic problem at time to infinity will transform to the elliptic problem. And elliptic problem for the one-dimensional case will become ODE. These are limits. Elliptic problem for one-dimensional case will become ODE. Elliptic problem for the one-dimensional case will become ODE. Hyperbolic equation at the time to infinity will remain hyperbolic. So these are the limits you should know. Parabolic equation at time to infinity will become elliptic. Elliptic for the elliptic will remain elliptic unless your dimension of the system is only one. The dimension of the system is one. The elliptic will become ODE, and the hyperbolic PD will remain hyperbolic PD even time to tending to infinity. And we have seen the generalized equation for the heat transfer, which is ux dou t dou x plus uy dou t dou y plus uz dou t dou z equals to minus k dou 2t dou x square. Minus or plus? Minus or plus? Is it plus? Plus. Plus k. Some heat generation. So this is generalized PDE. If you switch it off, it will be what I will do here. I won't put dou 2t dou x square. I put dou 2t dou x square plus dou 2t dou y square plus dou 2t dou z square. Plus. If this term is switched off, then the equation will behave as at the steady state. The equation will behave as this equation will behave as. Yeah, some people are all just buzzing, but nobody is actually having guts to say that yes, this equation will behave like this. This equation will behave like mixed elliptic hyperbolic system. Elliptic term is hyperbolic term. Okay. If there is no advection in the system, this term is switched off. Okay. There is no advection in the system. Okay. That means pure conduction problem is nothing but which system? Pure conduction. Pure conduction. There is no advection. Pure conduction. What is that? Parabolic. Excellent. Pure conduction is parabolic. Now, thing is that steady state no advection term. What is the system? Steady state no advection. What is the system? Steady state no advection. What is the system? Hyperbolic. How is it? Steady state no advection. Left hand side completely off. Left hand side completely off. Elliptic problem. Yes. Thing is that if the right hand side conductive term is gone, this time dependent term is gone, what the system will be? Hyperbolic system, first hyperbolic system. So this is the way the entire equation can be analyzed. This is the way the entire equation can be analyzed. Okay. So now we'll be going to some mechanism to solve the partial differential equation, and the partial differential will be solving by method of superposition. Before that, we'll be trying to categorize the problem. So method of superposition requires to categorize the problem. So we'll be talking about method of superposition. What does it mean? We'll have a problem, we'll split the problem. We have seen the split of the eigenvalue problem. Remember, last problem I did the splitting. The splitting means at a time one non-homogeneity will be there. At a time there will be one non-homogeneity. So number of non-homogeneity will be number of subproblems. Number of non-homogeneity will be number of subproblems. Okay? So if your boundary condition is non-homogeneous, differential equation is non-homogeneous, so that means there are two non-homogeneity. So at a time, one homogeneity will be there. If you take your differential equation non-homogeneous, boundary condition homogeneous, one sub-problem, you can take differential equation non-homogeneous, boundary condition homogeneous, another sub-problem. So, and each sub-problem can be solved, and for the sub-problem, I'll be trying to discuss three things. One is called EBC problem. Number two, I will talk about peak problem, and number three, I will talk about HIC, and none of the above will be called as NH. What is EBC? EBC means elliptic boundary condition. EBC means elliptic, please write down. EBC means elliptic boundary condition. That means EBC means equation is elliptic. Equation is elliptic, homogeneous, but BCs are non-homogeneous. This is called EBC. That means we have got the elliptic PD, elliptic homogeneous PD, but the boundary conditions are non-homogeneous. So in that case, we will try to demonstrate how to solve the EBC problem, and you can solve that particular. When you know how to solve the EBC, then you can particular sub problem. If you have an EBC category, you can solve it. So EBC problems are solvable. EBC problems are solvable. Number two is the peak. Peak means parabolic initial condition. Peak means parabolic initial condition. Equation is homogeneous. Parabolic, and subject to homogeneous boundary condition. Everything is homogeneous, subject to homogeneous BC, but non-homogeneous initial condition. Which is time dependency, but which means non-homogeneous initial condition. Initial condition means a time t equal to 0. If you want to know what is initial condition, which is nothing but time t equal to 0, which has to be non-homogeneous. Boundary conditions are homogeneous. PD itself is homogeneous, but non-homogeneous initial condition. At a time, one non-homogeneity will be there, as I said. Otherwise, you cannot solve a problem. PDEs at a time, even eigenvalue problems, you have seen that if PD is non-homogeneous, eigenvalue problems, that you have the requirement to have the boundary conditions homogeneous, otherwise you cannot solve. So similar manner, the PDE at a time, one non-homogeneity will be there. So if you look at parabolic initial condition, if the PDE is parabolic, you look at the boundary condition. Yes, my boundary conditions are homogeneous. Look at the initial condition, non-homogeneous. Okay, I can solve peak problem. Separate category. I will discuss how to solve EBC problem and the peak problem. Next is HIC problem, HIC. Hyperbolic initial condition. Next is hyperbolic initial condition, which is equation is hyperbolic. Equation is homogeneous, hyperbolic, homogeneous BC, but non-homogeneous initial condition. Exactly similar to peak problem, except instead of parabolic PD, we have got hyperbolic PD. Except instead of parabolic PD, we have got hyperbolic PD. So hyperbolic initial condition, this kind of problem has the homogeneous PD, homogeneous boundary condition, homogeneous PD, homogeneous boundary condition, and non-homogeneous initial condition. Okay, the equation is homogeneous, hyperbolic, homogeneous boundary condition, and the non-homogeneous initial condition. NH is basically called as non-homogeneous equation. So far what we have seen here, the PDE itself is homogeneous. EBC category, PIC category, and HIC category. If you look at EBC category, PIC category, HIC category, equations are themselves homogeneous. What will happen if the equations are non-homogeneous? Then the category called as non-homogeneous equation. So equation could be elliptic, parabolic, or hyperbolic, or non-homogeneous, but homogeneous, boundary condition or initial condition, or and whatever. So boundary condition, initial condition are homogeneous, but the equation itself is non-homogeneous. In that case, this can also be solved. This cannot be solved. NH. So this requires further superposition or splitting. Splitting technique is very, very important. Further superposition or splitting. So what we have to do for this type of problem, we have to see that whether you can divide again to get into EBC or P. So sometimes what actually happens, this type of problem, for example, for parabolic PD, non-homogeneous, what actually happens that NH problem can be again divided between EBC and P category. When we talk about elliptic and parabolic system, mostly we will be dealing with EBC and PIC. In chemical engineering, we don't deal with HIC. So no need to worry about HIC. We will be dealing about EBC and PIC. For the NH category, what we do that? When you see the equation is non-homogeneous, we cannot do anything. Then we have to split it further such that NH can be used to EBC and the PIC category. Because I will demonstrate in the class how to solve EBC and PIC problem. Then any partial differential equations are given. If you can get into EBC or PIC, even NH can be split up to EBC and PIC category. Any problems can be solved accordingly. Any questions? Any doubts? Because this type of concepts will be coming in the end semester. So there is only chance for you, the people who have not scored well in the quiz. Only chance to score further because that is very, very important. Okay, so we'll be taking typically one chemical reaction engineering problem. So after learning, so we'll be seeing this type of chemical reaction engineering problem. Dou Ca dt dou T equals to grad squared Ca minus K1C. A is going to be this type of reaction. A is going to be in a pore, this type of reaction going on. So pore, we have the pore diffusion term. Pore has the diffusive term, and this is a typical pore bed, and some of the part we have the Dirichlet boundary condition, and some of the part we have the Robins boundary condition. I call SD as Dirichlet boundary condition. SR means Robins boundary condition. If you don't write, when you go back home, you won't even know what is SD and SR. Many people are not writing what I am saying. SD here denotes the Dirichlet boundary condition, and SR denotes the Neumann's boundary condition. So this is a typical pore diffusion problem in chemical reaction engineering. Okay, the typical pore diffusion problem in chemical reaction engineering, and these are typical boundary condition. So if you do dimension analysis that you do at home, because you might have learned from your chemical reaction engineering. So what you can get in terms of dimensionless term, I will say T is also dimensionless, and we have grad square U minus, say, function of x1, x2, x3. Or some function of T. Some function is not constant. Remember, it is not constant. It's function of T. So the problem is formulated like this. This is your differential equation. you can see the differential equation itself is non-homogeneous. Non-homogenic part is here, which could be function of u, function of x1, x2, x3, it could be anything. It's non-homogenic part. Because if this part is not there, this equation says it is a parabolic PD, right? Straightforward. It's a resistive term. It has got the time dependency term. Of course, this is a parabolic problem. And there is no question of mixed parabolic, hyperbolic and all, because we don't have any advection term. If it is there, this is basically non-homogeneous parabolic PD, and we have to see how to solve it. So this requires boundary condition and initial condition. So u equals to ub on the display surface, and n dot grad u plus hu equals to ur on a surface. Okay, and ut equals to 0, so you say u0, function of x1, x2, x3. What are x1, x2, x3? You have a three-dimensional problem. My axes are x1, x2 and x3. These are my axes. x1, x2, x3. So this is the way overall problem has been defined. And what is Robin's condition? How can I write like this? I have discussed last class, minus k dou t dou x equals to h into t minus t. What we can write? We can write minus k dou t dou x minus ht equals to minus ht infinity. Okay, and you can see all plus you can put because of minus, and because this is nothing but so, and this is for the one-dimensional case. If you have the curved surface, this will be replaced. Actually, generalized condition of this is the heat flux. This is nothing but heat flux. This is nothing but heat flux. For one-dimensional case, you can write this way heat flux. For this type of case, what is the heat flux equation? If you have curved fluid, heat flux is like this. If you have a surface, we can say this is minus k dou t dou x. If you have this type of curved surface, how to define the heat flux? How to define the heat flux? What is the definition of flux? What's the definition of flux in terms of what's the definition of flux? What's called by this wrong definition. The wrong definition. Okay. So what actually I will say that you have a surface. So that's a normal direction. The unit vector, the normal direction is n bar. The unit vector, normal direction is n bar. Along this direction, how much heat or how much concentration is going? Okay. Along this direction, along the normal direction of a surface, any surface is there. You can easily find out the normal direction of the surface. How to find the normal direction of the surface? How to find the normal direction of the surface? See, I am talking about surface. How to find the unit vector? And the tangential direction, unit vector. What are we talking? I am talking normal direction or saying tangential direction, normal vector will occur. We are not to talk all those. What is the normal direction? Circle. What dot product? What normal direction is dot product? Normal direction is a vector. Come on, don't say dot product now. Normal direction is a vector. Any surface if I give, any surface f of x, y, z equal to constant. What is the normal vector? What is that? Somebody said grad something. Grad f is the direction of the normal. Grad f is the direction of the normal. So unit vector will be graded by mod of grad f. It's a unit vector. Right? Normal direction is grad f. The unit vector is graded by mod of grad f. So any such surface, we have the equation of the surface. But the surface equation is x square plus y square minus r square equal to 0. So circle equation is function of x equal to 0, which is x square plus y square minus r equals to 0. If you say grad f means, grad f is what? Grad f is dou f dou x dx plus dou f dou y dy. Right? And definitely we can see the direction of the norm. So it will be 2x dx plus 2y uy is the grad f. And the normal direction will be 2x Ex plus 2y ey divided by 4x square plus 4y square. Am I correct? That's it. So that is the way this n vector is calculated. Okay. So what's the heat flux? As I said, heat flux is along this direction. Okay. What's the definition of the heat flux from the Fourier's first law of heat conduction? Anybody can tell me what is Fourier's first law of heat conduction? Generalized way. We have done heat transfer. I am not asking something you do. What is Fourier's first law of heat conduction? Q equals to minus k grad T. Dou T dou x is the one-dimensional case. Three-dimensional case is minus k grad T, which is nothing but minus k dou T dou x Ex plus dou T dou y Ey plus dou T dou z Ez. Then how to write this k dou T dou x? Normal direction is what for this surface? Normal direction is what? For the one-dimensional case, what is their direction? Unit vector? Ex. So n dot q is nothing but Ex dot of this, and that's why you got minus k dou T dou x. That's the way normal heat flux is calculated. So normal heat flux is nothing but n dot q. That means along the component. What's the component of that? So if you want to find the component of a vector, you have to take a dot product in particular direction. You get the component. So the definition what you knew earlier is wrong. The definition is if you have a surface, you have the normal direction, along the normal direction, what is the component of the heat flux, and that is called along the direction. What's the component of the heat transfer rate? Is actually heat flux or heat transfer. So heat flux component along the normal direction is the definition of proper definition of the heat flux. Or not clear? So that's what this equation will be changed for this kind of surface. So it will be generalized equation. It will be n dot q1, which is nothing but minus n dot k grad T, and you can actually so q is minus k grad T, it is minus ht minus ht infinity and all will be plus, and that's what this equation is here. This is the most generalized Robin's boundary condition. The most generalized Robin's boundary condition. Van Dijk's clear? Yes? So Van Dijk's clear. So most generalized Robin's boundary condition is coming from the actual definition of the heat flux and the at the junction, the boundary. Okay. So this is the overall problem and how to solve. So what are the things there? You have non-homogeneity here. You have non-homogeneity here. You have non-homogeneity here. You have non-homogeneity here. There are so many non-homogeneities. Okay, so there are so many non-homogeneities in the problem. How to solve? How to solve the problem? There are so many non-homogeneities in the problem. How many non-homogeneities are there? There are 4 non-homogeneities, right? 1, 2, 3, 4. So first is non-homogeneity in the PDE itself. Second is Dirichlet boundary condition is non-homogeneous. Next is Robin's boundary condition is non-homogeneous. Next is time initial condition is non-homogeneous. How many non-homogeneities are there? How many? How many? Somebody is telling 2. That's what I am getting confused. How many are there? 4 non-homogeneities are there. Don't say 2 because I am sure you know how to count. 1, 2, 3, 4. If you ask me to start counting here, I don't know how to teach counting. It's a difficult problem for me. Maybe you should know number theory for counting. That also I don't know much. Okay, so there are 4 sub-problems. U1, U2, U3 and U4. And remember that finally U should be U1, X1, X2, X3 plus U2, X1, X2, X3 plus U3, X1, X2, X3 and plus U4, X1, X2, X3. There are 4 subproblems. And why can I do that? Because my operator is linear operator. If I have advection and a velocity is not known, velocity can be obtained from the Navier-Stokes equation. For an advection problem, I cannot use it because once you use the advection, which is u dot grad t, and if u is not known, the operator is becoming nonlinear. When you have advection, the operator is nonlinear and the superposition cannot be possible. And how to solve those kind of problems? By numerical techniques. By numerical techniques only you can solve. And that is good. And those kind of problems I am doing in my research. So our research is completely based on the advection, and there we cannot run an ideal solution. And because method of superposition is not possible, and in that case we have to go for the numerical techniques. Okay, so now we'll be going for the U1, U2, U3, U4. Okay? So for the U1, what we do, our equation will be non-homogeneous, but all are homogeneous. That's what I said. The split up at a time, one non-homogeneity will be there. So our problem is dou U dou t grad square U minus f of x1, x2, x3. Okay? Boundary condition, it will be U1 all the time. U1 equals to 0 on SD. Then n dot grad U1 H U1 equals to be how much? 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 See, this much time I have to tell this is the way your class is. 0, yes. On SR, Robin's surface. Next condition will be what? Next condition will be what? Initial condition is that U1 equals to 0 at t equals to 0. First sub problem is over. First sub problem is over. Next sub problem, U2. Now you tell me what will be U2? What will be the differential equation for the U2? Dou U2 by dou t equals to grad square U2. Homogeneous. We already discussed about non-homogeneity part, so non-homogeneity part will not be there. And what I will be having? I will be having initial condition non-homogeneous. So what will be boundary conditions then? What will be boundary conditions? U2 equals to 0 where? On steady surface. And then n dot grad U2 plus h U2 0 on SR, and then U2 equals to what? T0. U2 equals to U2 will be equals to what? U2 will be what? U2 equals to U0. And remember that what actually happens when you add it up, this is like your complete differential equation you satisfy, all boundary conditions will be also satisfied. That means boundary operator as well as the differential operator both has to be satisfied. That means U1 plus U2 plus U3 plus U4 should be UD at SD. Of course, it will be satisfied because U1 is already 0, U2 is already 0. Now next we consider U3, then U4. If U3 is only SD and U4 is 0, it is satisfied. That means this split up when you do, you should add it up and check the differential operator is satisfied, check the boundary operator is satisfied. Check the differential operator is satisfied and boundary operator is satisfied. Okay? So far we are doing fantastic. Next we go for U3. Tell me, you should now, you are now expert. Tell me what is U3. What is U3 then? Third sub problem. Dou U3 by dou t equals to grad square U3. Next, I will have the Robin surface. Robin surface I want to have on. That means U3 equals to 0 on SD. N dot grad U3 plus H U3 equals to how much? UR on SR, and U3 equals to 0 at T equals to 0 at a time 1 homogeneity. Last is display surface on. That means U4 is dou U4 dou T grad square U4. U4 equals to UD at SD. N dot grad U4 plus HU4 equals to 0 at SR and U4 equals to 0 at E equals to 0. Your job is to see whether everything is satisfied. If you look at dou U1 plus U2 plus U3 plus U4, dou T is nothing but dou U dou T. The left hand side is okay. Right hand side, grad square U1 plus U2, U plus U3 plus U4 there, and then if U1 is only there, or if x1, x2 is there, other part h is not there. So differential operator is peacefully satisfied without any question. Boundary condition, first boundary condition is Dirichlet condition. You see U4 is only non-zero, others are 0. If you add them up, you get UE. Next is n dot grad U. That means n dot grad U1 plus U2 plus U3 plus U4. So what you can do here, for this other condition, we have n dot grad U1 HU1 equals to 0, n dot grad U2 HU equals to 0, n dot grad U3 plus HU3 equals to U1, n dot grad U4 plus HU4 equals to 0. Add it up, you get n dot grad U plus HU equals to U1. Okay, not clear? And similar initial condition can be easily verified and satisfied. So that is the way after split up you should check a problem whether you have done the proper splitting of the problem. The splitting is not proper, then you may not get the correct solution. Now you have to categorize the problems. We have done this problem. This is the first type of problem, the second type of problem, third type, and the fourth type. First category problem is what category? You have the tools with you. Look at the toolbox and tell me the category of the problem. Look at your toolbox and tell me the category of the problem. First category is what? What is that? Non-homogeneous equation. Very, very correct. Second category? Second category? PIC. PIC says equation has to be homogeneous. Of course, there is no non-homogeneous term. Operator is homogeneous. Operator homogeneous means you know that what is L here? If I say L, what is your L operator here? Dou by dou T minus lambda square or minus grad square. Okay. Similarly, if you look at your L U1 itself equal to F, this is non-homogeneous term. This is what this problem. Parabolic homogeneity. Boundary conditions are non-homogeneous here. So this is what kind of problem? This is what kind of problem? This is not even NHE. Is it NHE problem? Is it NHE? So we don't know. We say category A. Another category is coming. NHE itself is not coming here. Yeah. But as I said that NHE or any category, you have to split again. No, but you cannot categorize as a non-homogeneous equation. Because non-homogeneous equation we can solve by finite Fourier transformation also. But this may not be. We have to see that. Okay? This is again category B type problem because we have the Dirichlet non-zero, Robbins zero and homogeneous boundary initial condition. So you have only one peak is identified, other sub-problems are completely gone. They cannot be identified. Other sub-problems are NHE, A category and B category. Okay? So NHE kind of problem, as I said, which can be solved by the finite Fourier transformation that I will be discussing after this. But, so this part, because this part cannot be categorized further into E, B, C or P, but this can be categorized. We will show that this category is an easier category than this category, the difficult category. So we will solve the non-homogeneous equation in the next section of the PDE when I will be discussing that, which is called as the finite Fourier transformation. Okay, which is called as finite Fourier transformation. So I will be now talking about the category A and category B type of problem, and we'll see further we can split category A and category B. Category A, what we have seen, dou U3 by dou T, grad square U3 equals to 0 at SD. N dot grad U3 plus HU3 equals to UR on SR, and U3 equals to 0. I think I have noted down correctly the point. What we'll do this problem, we'll split up when this kind of problem occurs, A or B type of category. That means this category maybe we should name as something which is called as, I can name this category as non-homogeneous boundary condition, NHB problem, right? So now in the class itself I have discovered a new category called NHB category. You have NHE and now you have NHB. For the NHB category problem, but the boundary conditions are non-homogeneous, but the other conditions are homogeneous, the technique, so we call as NHB category, non-homogeneous boundary condition. The entire problem can be split up two categories. One is the elliptic problem and the parabolic problem. So NHB category can be split up EBC and the PIC. So that means EBC plus PIC will give me NHB solution. And we know how to solve EBC PIC because I was discussing that one. EBC and PIC, okay, we can solve. That's what I said. EBC means no time dependency. Equilibrium problem, there is no time dependent part. That means we need to have a steady state component of the solution. The solution is steady state that can be fit in the EBC, and the rest of the part can be fit in the PIC category. So U3, if you look at very carefully, which is rho 3 of U3 x1, x2, x3, comma t. I am sure in thermodynamics we write all the variables. I am talking in terms of thermodynamics now. And grad square U3, which is x1, x2, x3, comma t. So now U3 you can write as x vector comma t, which can be written as W3 x bar t plus, let's see my symbol, plus V3, which is having only x. So V3 is having the time independent solution. That means V3 will be giving elliptic problem and W3 will give parabolic problem because V3 doesn't have time dependence. So that means what? What will be my sub problem? Problem 3, problem A1, problem 3A and 3B. Then I have 4A, 4B, right? U3 has the two sub problems. Tell me the problem in terms of V3. What could be V3? And V3 will give you what kind of problem? EBC or PIC? EBC. Now it is in your part. Give me EBC or PIC problem. Formulate EBC or PIC. Formulate EBC or PIC problem. What is that? Grad square V3 equal to 0. Excellent. It has to be because no time dependency. Then we have the condition here, NHB category, non-homogeneous boundary condition category. What is that? V3 equals to, what is the EBC? Please look at the class note. EBC says equation is homogeneous and boundary condition is non-homogeneous, and at a time one homogeneity will be there. Okay, so what will be grad square V3? V3 equals to 0. Next is, you can write here T equals to 0 and missed out, and n dot grad V3 plus HV3 equals to UR on SR. No initial condition. No initial condition because it is an elliptic problem. So this is now known as EBC problem. Am I correct? Next is this term. What is that? What is that? become my EBC to a peak problem now? What is my peak problem? Dou W3 by dou T equals to grad square W3. Next, W3 equals to 0 on SD. N dot W3 plus 3 equals to 0 on SR, and W3 equals to, then can it be peak problem? Of course not. You see the peak category. Peak category. It cannot be 0, 1, 0. It cannot be peak category then. How to do it? Now look into it. My U3, which is x vector comma t, which is W3, x vector comma t plus V3 x bar. Am I correct? That means what? U3 x0 equals to W3 x0 plus V3 x. U3 x0 equals to 0. That means what? W3 x0 equals to minus V3 x bar. We got the condition at t equals to 0, which is known as peak condition. Understood? Yes? Is that correct? So you got W3 equals to minus V3 x bar at t equals to 0. Okay? So this problem can be further divided, NHB can be further divided to EBC or peak, and similarly this problem can be also divided. So you can work out for the U4. Quickly you can tell me the condition for the 4A and 4B. I will do it here, 4A, 4B quickly. 4A, 4B. My category is U4, which is x bar t, W4, x bar t, V4 x bar. Quickly 4A, tell me, what is that equation? 4A, quick, no time. Grad square, V4 equals to 0, then V4 equals to, fourth problem, please look at, fourth problem. EBC problem, what is that? EBC, what are the conditions available here? This is 0 already, but this is not. So V4 equals to what? V4 equals to what? VUD. Is there the board? V4 equals to UD at h equal to SD. N dot grad V4 plus HV4 equals to 0 at SR, and V4 equals to 0 at t equals to 0. Am I correct? Yes. Next here, W4. Tell me quickly. W4 quickly. Who can tell? Dou W4, dou T equals to grad square W4. W4 equals to 0 at S equal to SD. N dot grad W4 plus HW4 equals to 0 at SR, and W4 equals to what? Minus V4 x bar at t equals to 0. Right? So that's it for today's class. Next class will be solving peak and EBC problems, and then the other problems can be solved. Thanks for your attention.